So what we're going to do now is we're going to take our hypothesis testing and our confidence intervals, and we're going to step it up just a tiny notch in terms of, instead of looking at a single proportion, we're going to be comparing two proportions. And in reality, it doesn't change the process for anything. You still follow the same approach. We still find p-values and critical values as needed. The only thing that changes is the test statistic, and also in terms of the confidence interval, that error changes. So it's a slightly different formula. And because we're working with two populations instead of a single, what we're going to be doing is using subscripts to denote which one comes from which population. So same process as before. I'm going to go through notation, the requirements that need to be satisfied, what the test statistic is, the methods that you can use, and then we'll do some examples of each. So starting out with the notation, what we're going to see is for all of these, we have this subscript of 1. So this is all going to indicate that we're dealing with this particular thing for our first population. If I change the subscript to a 2, that means it's the same parameter, but it's for the second population instead. So little p is always representing our population proportion. So in particular, this one is the population proportion for that first group of individuals, or that first population if it's something else. N1 is the size of our first sample. X1 is the number of successes in the first sample. And then P hat 1 is that sample proportion. So it's where you take the number of successes from the first sample and divide by that population size. And so it's that sample proportion for the first sample. And then Q1 is the opposite. It's the number of failures over the population size. So the way we find that is 1 minus that sample proportion. So the other word you'll often hear this called is the complement of P. Okay. And then if we use a subscript of 2, that will denote the second population. So all of the notations themselves still are exactly the same when we were working with one proportion. We're just adding this subscript to indicate this is the first or second population. In terms of the requirements, not much has really changed. You still want simple random samples. In this case, because you're dealing with two different things, each one of those has to be a simple random sample. The second thing is the one that's a little bit new, and this is that these two samples need to be independent of each other. So that's not a big deal for this first particular one, but when we start talking about dealing with two means, that does make a difference. So here what we want is those populations are not matched with each other. So one population doesn't impact the other. And then for the sample, we want there to be at least 5 successes and 5 failures, which was exactly that criteria we had before. So the way you find this is by taking that sample size and timesing it by your sample proportion. This needs to be at least 5. And when you take n and times it by the complement, that needs to be at least 5. So this guarantees we can get to that binomial distribution that we want. So our test statistic, what we're going to be working with is the same kind of hypothesis testing. Our main or our null hypothesis is that these two proportions are equal to each other. And then the alternate could be one is greater than the other, one is less than the other, or they're not equal to each other. It just depends on the context of the problem. But by doing this for our null hypothesis, if these two are equal to each other, their difference is going to equal 0. So what we're going to be doing when we're dealing with a confidence interval is we're going to see how confident are we in the difference of these two values? What does the difference lie between, okay? So the test statistic, I won't lie, it is a little gross looking. It does take a little bit more to actually figure out, but that's because we're working with more data here. So with our proportions, we always use that standard normal distribution table. So we're going to be working with z-scores. So our test statistic is some z-value. If you remember way back when we were dealing with a single proportion, we can kind of compare this test statistic to that one. So just to refresh on that, the test statistic for our regular proportions is the sample proportion minus the actual proportion, and then over the square root of P times Q over N. Okay. So if we extend that now to two proportions, what's going to happen in the numerator is we need to account for both of the sample proportions. So this is why we're going to look at the difference of the two. So we take the first population sample proportion and subtract the second. And then from here, we want to subtract the true proportion. So in that case, that would be the true P1 minus P2. Now the denominator is where it gets a little bit difficult. So it's still going to involve a square root, but again, I've got two samples here now. So what's going to happen is I'm going to have to work with potentially two different sample sizes. So this PQ over N, I'm going to need to kind of do for both of them. So what happens in the bottom is we have something called P bar, Q bar, over the first sample size. And then we're going to do the same thing with the second sample size to take everything into account. And this is specifically where this P bar, it's kind of like an average. Remember, that bar kind of represents mean typically, but it's not mean in the same sense. So what this is it's called the pooled sample proportion. You take the number of successes from each population and add them together, and then divide it by the total sample size. And then the way you find Q bar is just take that complement. You find the opposite value. So P bar ends up being 30%, Q bar is going to be 70%. And this P bar is called the pooled sample proportion. Okay. So once you have this test statistic, then you either go through and find the p-value or the critical values. So based on whatever confidence level that you want or significance level, you find your value of p using your standard normal distribution table or an online calculator, or you find those critical values and see does that test statistic fall into a rejection region. So same method applies for actually analyzing. This test statistic is just more complicated. The other thing we can also do is we can find a confidence interval for this difference. So we can see really how far off these two proportions are to each other. So the way we do that is if we want to find the difference, it's bound by that sample. So it's going to be the difference of those sample proportions plus some error, and then also the difference of those sample proportions minus some error, okay? So we can see how far off that estimate was. And this is specifically where this value of E, which is our error, again, it relates to the error when we were dealing with confidence intervals for proportions. It is going to be that critical Z alpha over 2. And then we times it by a giant square root. And really what goes in here is very similar to what goes in the bottom down there, that standard deviation estimate. So this is P1 hat, Q1 hat divided by N1. And then we're going to add that with P2 hat, Q2 hat over N2. We're going to start by just doing an example where we look at a test statistic and determine if we have a valid claim or not. And then we'll go ahead and do another example where we do a hypothesis test and then also use a confidence interval to test a claim. So you can kind of see really they go hand in hand. So the example we're going to start with, we're told a newspaper published an article about a study in which researchers subjected laboratory gloves to stress. Among 260 vinyl gloves, 61% leaked. Among 260 latex gloves, 13 leaked viruses. Using a 5% significance level, we're going to test the claim that vinyl gloves have a greater leak rate than latex gloves. And we're going to let vinyl gloves be population 1. Okay? So we're making a comparison between these two different types of gloves. It happens to be that they have the same size, but it doesn't need to be. So I have one set of parameters for vinyl gloves, and I have one set of parameters for latex gloves. They tell us to let vinyl gloves be population 1. So this tells me the sample size of my first population is those 260 vinyl gloves. So N1 is 260. And then that sample proportion, the percentage that leaked, is 61%. So that is 0.61. And then the proportion that didn't leak is 1 minus that. So that would be 39%. Okay. The other thing we're also going to need, which really helps us verify those requirements, is we need to figure out what is X1 and X2. So that's that success rate. So what we need is we might as well just figure that out right now. This is the number of successes. So what we do is we take the sample size and times it by the percentage that leaked. So I'm going to do N times P. So I'm taking the 260 and timesing it by 61%. And then we do have to round here. This is about 159. So 159 out of 260 gloves leaked. And what I needed is I needed this to be greater than 5, and fantastic, that is. So we also need N times Q to be greater than or equal to 5. But 260, 159, there's 100 left over that didn't leak, so I'm good there. Now for the latex, that sample population is the same size by chance, doesn't have to be. And here the proportion that leaked is 13% instead. So its complement, the amount that didn't leak is 1 minus that amount. So 87% did not leak viruses. And then we need X2 as well. So that's where I take the entire population and times it by 13%. And this gives me about 34 gloves out of 260 that leaked, which is fantastic because that's bigger than 5. So the amount of gloves that did not leak is around 230. So fantastic, that's greater than 5. And then you can assume the rest of the stuff is also holding true, okay? So what I want to do is I want to write the claim first, and then I want to figure out what is my test statistic. We'll have to use our Z tables to figure out area to the left of the curve and do everything from there. So the claim is vinyl gloves have a greater leak rate than latex gloves. So this proportion is bigger than this proportion. Okay, so that is our claim that we want to test. The proportion that leaks for vinyl is greater than the leakage for latex. So since this does not involve equality, that means this is the alternate hypothesis. And the null hypothesis is that these two proportions are equal to each other. Or again, the way you can think of it is this proportion is less than or equal to the other, okay? So in terms of the type of test that I'm doing, my alternate hypothesis is that one is greater than the other. So that leaves an area over here. So this is going to be a right-tailed test. And the significance level they tell us is 5%, okay? So I need to find my test statistic, but before I can even do that, I need to find those pooled sample proportions. So I'm gonna start by finding those. So P bar is going to be, we add up the number of successes and then divide by the total sample size between the two. X1 we found to be 159. X2 we found to be 34. And it happened to be both of these have the same sample size, which is 260. So this gives us 193 out of 520. And then this unfortunately is a decimal, so we do need to round. Really 3 decimals tends to be enough. You can always use more. You have tolerance in homework, but the more decimal you use, it tends to be better. But if I use 3 decimals, you'll see this does come out perfectly fine. Okay. So this pooled sample statistic is 37.1%. So when I go to find the complement, I do 1 minus this amount. So 1 minus 0.371 will give us 0.629. Okay. So I have everything I need now to actually find my test statistic. So the way we find this is we look at the difference in sample proportions. We subtract what is that true difference, but automatically I'm gonna go ahead and mark this off. We're saying the claim is that, or the null hypothesis is that these two are equal to each other. So this is going to be 0, which saves us a little bit of effort. And then in the bottom, I have a giant square root, and we go ahead and multiply these sample pooled proportions and its complement divided by the sample size of the first sample. And then we do the same thing with the sample size of the second sample, okay? So plugging all our numbers in the top, the first percentage is 61%. For latex gloves, that sample is 13%. And then we just figured out these numbers on the bottom. P bar is 0.371. Q bar is 0.629. And then N1 is going to be 260. And it happens to be the same thing for the second. In the top, it'll always be, but in the bottom, it happens to be the same sample size. So definitely very tedious to plug into your calculator. You can use your phone, but I would highly, highly, highly recommend a handheld calculator. So I'm gonna do my best to do this on the calculator on here. Again, handheld works way better as opposed to your phone calculator. And then really from here on out, I'm gonna use Desmos Online because that'll be a little bit cleaner. But at least to show you how you can do this, first, if at least I do the top part, if I do 0.61 minus 0.13, that's gonna give me 0.48 in the top. And then in the bottom, I've really got exactly the same information. Okay. So I'm gonna go through the bottom value, and what happens is I actually have this button that's 1/x. So once I figure out what the bottom equals, if I hit that button, it'll flip it to the bottom, and then I can times it by 0.48. So just to show you, just like if I had, say, 4 divided by 2, the bottom is 2, so I'm going to flip it, and that makes it 0.5. So dividing by 2 is the same thing as multiplying by 5, and you still get the same answer. Okay? So I'm going to go ahead and figure out what this denominator has to be. So I need to take 0.371 times that by 0.269, and then I'm going to divide that by 260. And then really I need to add the same thing, but I have to be careful here. I'm going to put all of this in a single line inside some parentheses. So I need 0.371 times 0.629 divided by 260. And so that's everything inside my square root. So now I'm going to take the square root of that, and it gives me this value. And now I want to flip it in the denominator. So this is where I press that 1/x button. So basically now that's going to give me 1 over the bottom. I'm going to times that by 0.48. And so my test statistic is about 11.33, rounding to 2 decimal places. Okay. So like I said, not the prettiest to do in this calculator. Definitely using something that you have a visual screen on will be much better, like a TI-30XS. Those are great. Okay. So now that we have our test statistic, now we need to figure out what is the area to the right of this test statistic. And if it is less than 5%, we know that's significant and we're going to reject that null hypothesis. Okay. So using the Z table, which is at the very end of this PDF, the area to the left of Z equaling 11.33 is the following. So to give you that picture, here is our test statistic. I want to know what this area is, because if it's less than 5%, that means it falls into the rejection zone. If it's more than 5%, that means the rejection zone is inside of it, and I can't, or I don't have enough evidence to support the claim. So using our Z table, if I go all the way to the bottom, the biggest value I have is 3.99, because anything after that has an area to the left being 1. Because this is 11 standard deviations away from that mean. So the area to the left of 11.33 is 1.0000. So our p-value is 1 minus this, which gives you 0. And then you can fill in the extra decimals if you really need to. But it's such a small, small, small area. So that is this amount. So because that happened, since our value of p is smaller than our significance level of 5%, this tells us to reject the null hypothesis. Okay. So if I go back to what that null hypothesis was, it was that the two proportions are equal, meaning they leak viruses at the same rate. But in this case, we're rejecting the null hypothesis, so there's sufficient evidence for our actual claim, which is that vinyl gloves leak more viruses than latex. So here, there is sufficient evidence. To support the claim that vinyl gloves leak more than latex. So now that we have a little bit of a hang with this particular method, we're going to go through another example. We're going to still use a hypothesis test, still going to find p-values for it, but we're also going to go through the claim using a confidence interval as well. So this way we can see how to find that. So for this particular example, since an instant replay system for tennis was introduced at a major tournament, men challenged 1,442 ref calls, with the result that 429 calls were overturned. Women challenged 763 referee calls and 224 were overturned. Using a 5% significance level to test the claim that men and women have equal successes in challenging calls. So again, I have two populations, one being men, one being women. It doesn't tell me to make one versus the other, so I'm just going to go in order. We're going to call men the first population and women the second population. So for men, that sample size is going to be 1,442, and the number of successes they actually give us this time, 429 of those calls were overturned. So this proportion is 429 out of 1,442. So this gives us roughly about 29.8% of calls being overturned. So I also need its complement, so I might as well find that. We take 1 and subtract the 29.8%, which gives us that 70.2% of calls were not overturned. For women, this is now a different sample size. So there were 763 challenges, and of those, 224 were overturned. So the sample proportion for this population is 224 out of 763. So rounding that to the same number of decimal places, around 29.4% were overturned. So that complement is 1 minus 0.294, giving us that 70.6% of calls were not overturned. So the claim is that men and women have equal success in challenging calls. So our claim is that these two actual proportions are equal to each other. So since we have equality, this is our null hypothesis, which means our alternate is they are not equal to each other. Okay? So in this case, when I go to find this test, this is a two-tailed test. So I'm going to be looking at these particular regions, and I'm going to need to find my test statistic. And if the area in these regions is going to be more than 5%, I'm going to reject this claim. So we need to find our test statistic first, whether we do p-value or whether we do a critical value. So let's go ahead and find that. So if I find my pooled sample, I need to add the number of successes together and divide by the total of the two samples. So the number of successes is 429 and 224 out of a sum of 1,442 and 763 challenges. So if we add those together, it gives us 653 out of 2,205 calls being overturned. So summing them together, I'm going to go out more decimal places here. This is about 0.29615. So the complement of that is 1 minus this amount, which gives us a total of 0.70385. Okay. So we now can find our actual test statistic, writing down what that is. It is the difference in those sample proportions minus the difference in the true proportions. But again, our claim is that these are equal. So this is 0. And then in the bottom, I got a big old statement, which is going to be those pooled samples times the complement over the first sample size, and then the same thing over the second sample size. So before I pull up the calculator, I want to go ahead and I want to put all of these numbers in. P1 hat is 0.298. P2 hat is 0.294. And then in the bottom, I need a lot of room here. P bar is 0.29615. Q bar is 0.70385. And then N1 is 1,442. The numerator here, exactly the same thing. But then N2 is going to be 763. So this would definitely be difficult in your hand or in your phone calculator. So we're going to go online and use Desmos's Scientific. So even here, this isn't the best to type. So I'm going to start by putting my fraction. In the top, I've got 0.298 minus 0.294. In the denominator, I have a square root. My first thing is a fraction, so I'm going to go ahead and put that. We've got 0.29615 times 0.70385 in the top. In the bottom, 1,442. And then I need to add to that another fraction. So let's go ahead and do our division to get that fraction in there. We got the same thing, 0.29615 times 0.70385. And in the bottom here is 763. So if I round this to 2 decimal places, that would be 0.2 because it would bump up. So my test statistic Z is about equal to 0.20. Okay. So we can use p-values, we can use critical values. Again, it doesn't matter. I think in this instance, p-values are a little bit simpler. But what I want to figure out, if here is my test statistic of 0.20, I want to know what is this area here. And because this is a two-tailed test, that particular area is P divided by 2. Because this area over here is the same, this is also P over 2. Okay. So I need to figure out the area to the left of this test statistic, and then we're going to be able to figure out the area to the right and double it. So here, the area to the left of 0.20 is the following. So moving on to my Z tables, the area to the left is 0.20, so 0.20, it's 0.57926. So the area to the right is 1 minus that. Which is 0.42074. Okay. So our actual p-value is going to be 2 times this amount because of symmetry, which gives us, rounded to 3 decimal places, 0.841. So in this case, what that means is our rejection region is actually a smaller area because our rejection region should only be 5%. So since our p-value is bigger than the rejection region, we're going to fail to reject the null hypothesis. So since p is greater than or equal to alpha, which is 5%, we fail to reject the null hypothesis. So there isn't sufficient evidence to warrant rejection of the claim that these two proportions are equal to each other, so men and women have the same success rates. So it doesn't mean we accept that hypothesis, but there is not evidence to reject it, okay? So we're gonna do really the exact same thing now, but we wanna test the claim using a confidence interval. So what that means here is I wanna see what do I think the difference in these proportions lies between using a 5% confidence level, okay? So to refresh on this, we're estimating it by the difference in those sample proportions, but we know there's some error because this isn't the full population. So to find that interval, we add the error and then we subtract the error. And specifically, this is where the error E is found by taking that critical Z value and timesing it by a square root. And in this case, what goes inside is P1 hat, Q1 hat over the first sample size. And then the same thing with the second population over its sample size. Okay. The way we find Z alpha over 2 is using our Z table. So I'm going to draw a picture. We do have a little chart though that's available in our previous notes. But here, if I've got my standard normal distribution, I have these two cutoff values because it is still that two-tailed test. And this value here will be a positive Z alpha over 2. And then from the symmetry, this is the same one, but negative. And our actual area that we want these two to be is 0.05. So that means the area in each tail is that divided by 2. So it should be 2.5%. So this area should be 2.5%, and this area should be 2.5%. So you can use the table to find this positive one because that's the one we want to go here. In that case, you would look for what is the Z value that gives you 97.5% or 0.975. However, you can also find the negative one and then you just make it positive. Okay. So if I go to my table, my negative one I think is a little bit easier to spot because you want 0.025. So if I look around here is where I start to get 0.02. So if I search for 0.025, that would be right here. So the negative Z value is negative 1.96, which means the positive Z value is positive 1.96. So using our table, negative Z alpha over 2 is negative 1.96. So positive Z alpha over 2 is just the positive case of this. So that's the value I'm going to plug in here for Z alpha over 2. and then all of these other values are the same as before. So we can actually find our error. I'm going to start by just copying this formula down. And then we'll go ahead and we'll fill in all of these pieces. So the first is 1.96. Then we're going to times that by a giant square root. P1 hat is 0.298. And then Q1 hat is 0.702. And that first sample size is 1442. Then for the second population, that proportion is 0.294, and its complement is 706 over 763. So I need to use a calculator again. So we can plug this all in one shot. We got 1.96. We want to times this by a giant square root. My first bit is a fraction. You don't need to type that 0. You can just type 0.298. Just to show you can type the 0 in as well. And in the bottom, it's 1,442. Then I need to add another fraction, which is 0.294, times that by 0.706, divided by 763. So rounding the 3 decimal places, the error is about 0.040. So I'm going to add and subtract this to the actual difference to get a 95% confidence interval for the difference in the true proportions. Okay. So we'll go ahead and do that. The 95% confidence interval and you can do it by a single one where you just do P1 minus P2 hat plus or minus the error, but I'm just gonna go ahead and write the whole thing out. So the difference in these two proportions is bounded above by those samples plus some error, which is 0.04, and then the same thing, the samples minus an error. So our true difference in proportions is starting with the first one. This is 0.298 minus 0.294 plus the error, which is 0.040. And then really on the opposite end, you do the same thing, but instead of adding the error, you subtract it. So the difference between our sample proportions is really going to be 0.004. So we're going to add 0.04 and we are going to subtract 0.04. So when I subtract them, that gives me negative 0.036. And then if I add them, that gives me 0.044. So that tells me the true difference in these two falls somewhere between these two particular values. So my claim is that these are equal to each other. So that would mean the true values or the true difference is equal to 0. Well, if I look at my confidence interval, that's somewhere between a negative value and a positive value, their difference equaling 0 falls inside the interval. So that tells me there is a chance that they are equal to each other with a decent probability. So because of that, we reject the claim. If it happened to be that this one was positive 0.036 and positive 0.044, 0 doesn't fall inside those particular values. So in that case, their difference is something positive, so there is no way they are going to equal each other, okay? So that would tell me I would reject my null hypothesis. And likewise, if this one was negative, that tells me the difference between them is negative. And so that would mean this has a higher portion than this one, okay? So, but in this case, because 0 falls in my confidence interval, there does not appear to be a difference between the two proportions. So there is not sufficient evidence to support rejection of the claim. Okay. So what you're looking for is, does your confidence interval contain 0? If it does, you can't support the null hypothesis, or you can't support rejection of it. If it does not contain 0, then you can support rejection of it, okay? So we're going to continue to do the same thing just with means. We're not going to worry about testing 2 standard deviations. That is quite messy. But we have to talk about whether means are independent or dependent samples, because that's going to make a difference.